Material absorption losses in silica glass fibers. Material absorption is a loss mechanism related to the material composition and the fabrication process of the fiber, which results in the dissipation of some of the transmitted optical power as heat in the waveguide or fiber. The absorption of light may be intrinsic, which is caused by the interaction with one or more of the major components of the glass, or extrinsic. That means the portion caused by impurities within the glass. So basically we have two kind of material absorption. One is intrinsic, another is the extrinsic. Let us consider the intrinsic absorption. An absolutely pure silicate glass has little intrinsic absorption due to its basic material structure in the near infrared region. But it does have two major intrinsic absorption mechanisms at optical wavelengths, which leaves a low intrinsic absorption window over 0.8 to 1.7 micrometer wavelength region. That is, one is this one, another is this one. So these are the two ranges where you can see that the absorption is quite high. Here we have high absorption, here we have high absorption. So within these two wavelength, we have some lower attenuation right here. So we can use this portion of the frequency or wavelength where the attenuation is lower, and its range is more or less 0.8 to 1.7 micrometer. So another part is the Rayleigh scattering. We will discuss it later on. The total loss, if we consider these two, it will be like this one. So as you can see, photon energy when it is nearly 2 electron volt, then the absorption is quite high, and energy when it is less than 0.8, like 0.7 or 0.6, the absorption is again very high. So within that region we have some lower attenuation window right here. Extrinsic absorption. In practical optical fibers prepared by conventional melting technique, a major source of signal attenuation is extrinsic absorption from transition metal elements impurities like chromium, copper, nickel, etc. But one of the most important extrinsic loss uh, mechanism is caused by absorption due to hydroxyl ion, which is dissolved in the glass. These hydroxyl groups are bonded into the glass structure and have fundamental stretching vibration, which occurs at wavelengths between 2.7 and 4.2 micrometer depending on group position of the glass network. The fundamental vibrations are give rise to overtones appearing most harmonically at 1.38, 0.95 and 0.72 micrometer. So if we observe the characteristics, attenuation characteristics for hydroxyl group, then you can see we have a peak attenuation at 0.72 micrometer. Another peak is around 0.95 micrometer, and here we have another peak around 1.4 micrometer. So if we consider the overall attenuation characteristics, you will see we have different type of absorption like ultraviolet absorption or ultraviolet band edge. We have infrared band edge. There are certain absorption related to the waveguide imperfection, which is almost constant or independent of frequency, and there is another kind of absorption, or it is not absorption, it is the attenuation. Actually it is a kind of scattering. Because of that, the light wave, instead of going to the destination, it used to go in the other directions. So it is a Rayleigh scattering. So its characteristics is like this. So if we consider all these things, we have the experimental characteristics of the attenuation characteristics of the glass fiber, and you can see that we have a huge amount of absorption right here, which is due to the hydroxyl ion, right? And we have a valley right here. We have minimum attenuation right here. Okay, so around 1550 nanometer or 1.5 micrometer, we have a valley or low attenuation region. Around 1.3 micrometer, we have another valley. So these are called the windows where the attenuation of the glass fiber is comparatively lesser, and we have to use those windows for communication system. This chart is showing some ITU spectral band definition and their band designation. So it is the original band or O band, and its range is this 1.26 to 1.36 micrometer. All the wavelengths are measured in micrometers. Next we have extended band E band 1.360 to 1.460. Then short band or S band 1.460 to 1.530. Then conventional band or C band 1.530 to 1.565. Long band or L band 1.565 to 1.625, and ultra long band or U band, that is the 1.625 to 1.675. So these are some band designation used in as per ITU standard. Three major spectral windows where fiber attenuation is low, that is, these three windows are very important. The first window is nearly at 850 nanometer with attenuation of 2 dB per kilometer. Second window is at 1300 nanometer with attenuation of 0.5 dB per kilometer. And the third window is 1550 nanometer with attenuation of 0.3 dB per kilometer. So as you can see, first, second, and third window, among all these windows, the third window, for the third window, the attenuation is lowest. So 1550 nanometer windows is the standard windows for today's long haul communication system. So this particular frequency or this particular wavelength is used nowadays for long haul communication.